Great. So apologies for the delay. I had some difficulties with my PowerPoint presentation, so I'm just gonna show it here in PDF format. Shouldn't matter too much. So the paper I'm going to talk about is this work called AutoAugment, which is about learning augmentation policies instead of handcrafting them, and was done by these people at Google Brain. So why are we interested in data augmentation? Well, it allows us to make better use of limited training data. So it's something that's only useful if the amount of training data that we have is limited. And it allows us to increase the amount and the variety of training data. Another way to think about data augmentation is that it allows us to teach our model some invariances that the data distribution has. So for example, if we want to recognize cats, we think, or if we want to distinguish between cats and dogs, we think it doesn't matter whether the animal is in the top left or in the bottom right corner, and we can teach this to the model by shifting or by slightly moving the image. So how is this done? Traditionally, data augmentation was done by manually designing dataset specific augmentations. So examples would be distortions or translations and rotations. But the drawbacks of this method is that it requires expert knowledge and time. So it's labor intensive to find optimal translations. So what they want to do instead is automatically find a data augmentation policy directly from the data, and the method which they use for this is reinforcement learning. So now they have to, of course, they still have to think about what the space of policies is which they search, like what are the policies that they consider. And in fact, they consider policies that consist of 5 sub-policies. And then whenever they have an image, they choose one of these sub-policies at random. And each of these sub-policies in turn consists of 2 image operations which are applied sequentially. And each of these image operations is described by a probability of applying and a magnitude. So for example, by how much to turn your image. There are some transformations that don't have a magnitude, like a left-right flip, but most of them do. And so the set of transformations which they consider is all of the transformation in the Python image library, which are image to image. In addition, they look at cutout and sample pairing, which we're going to look at in a minute. So they use 14 transformations from the Python image library together with these 2 transformations, which gives them a total of 16 transformations. So each policy consists of 5 times 2 equals 10 sub-policies. So they search for, they have 16 possible transformations. Then 10 and 11 are, so they have to find the optimal probability magnitude. And so in order to search these, they discretize the number of possible probabilities in magnitudes into 10 and 11 possible values. So this gives them per sub-policy 16 times 10 times 11 possibilities. And then there's 10 sub-policies. So the full search space is on the order of 10 to the 32 possible policies that they search through. So here are these 16 transformations that they consider. Some of them are related to like the colorization of the image. Some of them are more geometrical, right, like rotate or shear. So again, these top 14 transformations are from the Python image library. Then there's cutout, which just sets a random square to gray, which was described in another research paper. And sample pairing, where you linearly superimpose different training images. So here is an example of a policy applied to the same image different times. So this is an image from the Google house number dataset. There, as I said, each of these policies consists of 5 sub-policies. And because each of these sub-policies in turn is stochastic through the through the probability of applying, the transformed image looks different in each batch, even when the same sub-policy is applied. Okay, so how do they train this? Well, there are actually 2 distinct networks. There's the controller, which is a recurrent neural networks. And this is the network which is actually trained through reinforcement learning. The controller has to make 2 times 5 times 3 predictions. So for each of the 5 sub-policies, which has 2 transformations each, it has to make 3 predictions, which are which transformation to apply and the probability and the magnitude. So this controller is what is trained through reinforcement learning. And in order to get the reward signal for reinforcement learning, they then train a child model, which is a wide ResNet. So what they do is the controller makes this prediction, which describes one augmentation policy. Then they use this policy to train the child model from scratch. Then they test its out-of-sample performance, and this serves as the reinforcement, as the reward for the reinforcement learner. So each gradient update of this controller involves one full training of this child model of the wide ResNet. And in the very end, when they actually test how well they have done, they concatenate the 5 best policies such that it then actually consists of 25 sub-policies. As I mentioned, for each gradient update of this controller, they train the child model from scratch. Because they have so many, because they have 5 sub-policies, and each of them is only used 1 in 5 times, they train for a total of 120 epochs, such that each of these sub-policies is applied many times. And this is only for training, for finding the policy, and then in the end, once they have found a policy and want to see how well it actually does, they train for much longer, so for several hundred epochs. For training, they use cosine learning decay with a single cycle. I mentioned that this this space that they search in has on the order of 10 to the 32 policies. And during training, they sample around 50,000 of these with reinforcement learning. So a tiny fraction, but still it's actually not clear whether the policies they find are better than what could be found with random search. And I found this to be quite surprising. So they explicitly write, it might be possible to use a different discrete search algorithm, such as genetic programming or even random search to improve the results in this paper. So I was quite surprised that they didn't compare the performance of the reinforcement learner with simple random search, which seems like the most obvious and trivial baseline and would be like also so trivial to code compared to the reinforcement learner. So I really don't know why they didn't just compare it to random search and see what it actually does better. So the first data set that they use it on is what they call reduced CIFAR-10. So CIFAR-10 has 50,000 images in it or in the training set, and they only train on 4,000 of these. And the reason is what they mention here. We find that for a fixed amount of training time, it is more useful to allow child models to train for more epochs rather than train for fewer epochs with more training data. This is something which I personally found somewhat surprising and counterintuitive, but it's what they found. So here's how they actually augment their images. So you see here that the AutoAugment, which I've described so far, is only one step in the full augmentation pipeline. So they first start with some baseline processing, which are just things which they think are kind of guaranteed to help, which are proven. So they standardize the images, include left-right flips, and zero padding and crops. Then only the second step is the policy which they learned and which includes cutout with some size that is learned. And then in the end, they apply cutout again with a fixed size of 16 by 16 pixels. So in principle, it's possible that they apply cutout twice if the learn policy applies cutout, but they comment that most policies which they find do actually not make use of cutout, so usually they only apply it once. On CIFAR-10, they find that the good policies mostly use color-based transformations, so transformations which work with contrast and brightness of the images. On the other hand, geometric transformations like share are rarely chosen, and invert is almost never applied. What invert does is simply basically change black and white. So here in the example policy before, we saw some examples of invert. So for example, here. Okay, and so these are the results that they get. They find that they pretty consistently outperform both the baseline augmentations and cutout, and they get results which they claim are state of the art. Now they work with a number of other data sets, and I won't go into detail with all of them. So just a few remarks. They then they apply to CIFAR-10, which, as the name says, has not only 10 classes but 100, and they actually use the same policy that they found on reduced CIFAR-10 to then train on CIFAR-100, and they found that this works well. So these policies can actually be learned on one data set and then transferred to another data set. Then they look at the street view house numbers, which we already saw an example of. Here, unlike in CIFAR, they found that these two, the invert and the shear transformations, are the most useful. And yeah, if you look at these images, I think this makes some intuitive sense. Like if you have an image which shows a house number and you invert it, it's still a recognizable house number. And similar, you probably naturally get some shearing effects because of the perspectives from which you take the photo. And then in the end, they also train it on ImageNet, and they find, probably not surprisingly, that good policies on ImageNet look similar as those on CIFAR-10, which means that they mostly use color-based transformations. And on all of these data sets, they basically achieve state-of-the-art performance. They also want to test in more detail how transferable these policies which they learn are. So they apply them on 5 so-called fine-grained visual classification data sets. One of them is the Stanford CAST data sets, for which they claim that they find the best results so far. So by simply using the augmentation policy which they learned on CIFAR, they find a new best result for Stanford CAST with an error rate of approximately 5%. Yeah, so they say that they found that basically training one policy on one data set and then transferring it to another data set basically never hurts performance of the models. And they say that this is in contrast to some other augmentation policies, like, for example, simply doing cutout without anything else. And again, not too surprisingly, they find that policies are the better, the more similar the two data distributions are. Finally, I have said that they consider policies with 5 sub-policies. They then study how the number of sub-policies, what the effect of that number is, and whether having multiple sub-policies actually help. And they find here that using up to 20 sub-policies actually helps the validation error. But maybe it's worth remarking here, yeah, that they train for 200 epochs, which is necessary if you have this number of sub-policies. Like if you have here 100 sub-policies and you train for 200 epochs, then each of these sub-policies will be applied only twice for each image, on average, of course. Yeah, so this was already my last slide. Do we have any questions?
Great presentation, Adrian. How did they deal with the like the continuous aspects of these transforms? Like, you know, I can rotate by a certain number of degrees. So was that in the action space of the agent?
Right, yeah, so they discretize all of the transformations. So here in this number, I think 10 is the number of possible values that they discretize the magnitude into. So for example, here the sharing goes from -0.3 to +0.3. So they discretize this interval into 10 values. And similarly, the probabilities which go from 0 to 1 are discretized into 11 possible values.
And in terms of speeding up the evaluation of the fitness of the candidate, so it seems like the only tricks they used were train on a subset of the data and train fewer epochs. And then when you find a good candidate, then take that good candidate and train it to convergence. Is that right?
Sorry, could you say it again?
So one of the challenges is how fast you can evaluate a candidate, right? That's what you've been calling the submodel, I think.
Right.
They train on a subset of data, so that speeds it up.
Right.
They train on fewer epochs, but then if something looks promising, it has a high fitness, then they train that to convergence. They train it for more epochs.
I think on every step they train for 200 epochs. So.
Oh, it's always uniform. Okay.
Yeah.
Interesting. So one of the tricks here is like the use of a surrogate model, like having a model that can predict the performance of a candidate.
Right.
Which they didn't use anything like that, huh?
Well, so I guess that's the controller which over time learns to choose useful policies.
I see. Yeah, that's just an agent brain, basically.
Yes, for each update of this controller, they train the whole ResNet from scratch for 200 epochs, and hope that this controller learns to find policies that work well.
What's the parallelization opportunity here? Like how many of these wide ResNets can you train in parallel?
Well, the way they described it is quite sequential, like, because yeah, for each step for each update here for the controller, you have to train again one from scratch, one ResNet. So it seems that there's not too much parallelization that you can do, unless you do some. I guess you could do the updates of the controller in batches, but this is not something that they mention.
Mm-hmm. Yeah, this is where probably if they had done a random search or had done, like, as you mentioned, like an evolutionary algorithm or something like that, it could have been parallelized probably much better, and you probably would have seen much more of this space than what this agent saw.
Right.
I had a question. Do they actually change out the validation set from time to time? Because it seems that it might be possible that there might just be overfitting to the validation set.
So they certainly don't comment on changing the validation set over time. And of course, I guess that's also, you also have to be careful about that, because you don't want to use images which earlier you used in your training set, use them later in your validation set. So this would be even worse overfitting. Yeah, I guess it's definitely a concern, but I think the fact that they show that they can actually transfer these learned policies shows to some degree that they didn't overfit too badly to the validation set.
Mm-hmm. Yeah, okay.
Yeah, but I think it's certainly a valid concern.
Is there any like domain adaptation of this agent, like having learned, like if you trained on CIFAR-10, does that agent then converge faster? Does it perform well on ImageNet or something like that, or you have to run this? You have to train basically in the domain that you're applying it. Like, is this a general purpose, augmentation agent, or is it specific to a data set, basically?
I think what they do is they only transfer the final policies, so only like the output. And yeah, I guess what you suggested would be to first train the controller on CIFAR and then fine-tune it on ImageNet or something like that.
As an example, yeah, because ImageNet evaluations are even more expensive. So if you can train that agent fast, right?
This is not something which they do. Yeah, so what they do is they only transfer the policies, or like the final output of the controller trained on CIFAR, and then use that on ImageNet. But that would, yeah, certainly be an interesting thing to try.
What sort of lessons do you think that someone who doesn't have access to Google level of compute, like you can't train a ResNet model to completion for every gradient step for an agent, at least most normal people can't. So what sort of lessons do you think someone like us should be like taking away from this sort of thing?
Yeah, it's certainly also a valid question. Yeah, because I think, as you said, so I mentioned they try 15,000 different policies, and for each of them they train for 200 epochs. So the amount of compute that they use is enormous. I think they do make an effort to make it as useful for people like us as possible. Because, for example, yeah, they describe qualitatively what kind of transformations work well. As I mentioned, they say that on ImageNet and CIFAR, the color-based transformations are most valuable. They also, they actually provide in the appendix the actual policies with the magnitudes and the probabilities that they found on CIFAR and ImageNet. So there's actually nothing stopping you from using these policies. If you happen to want to train on CIFAR or ImageNet from scratch. But I guess these might also be useful for fine-tuning.
Awesome. Thanks for doing this. That was a great presentation.
Sure, thank you.
Yeah, it is. I agree with Virat, right? It's a little bit underwhelming. Like they discretize the action space of the agent, and they're not convinced that this is even better than random search. Like, with this amount of compute being burned, you would think that this would come up with like completely novel transformations that we've never even heard of or tried. That's directly maybe manipulating the pixels of the image or something like that. But it's, for the amount of compute, it's pretty underwhelming results.
I think that's also a fact caused by the fact that they've limited the sort of state space for the agent by just discretizing the magnitudes and the probabilities that the agent can see in. Sort of.
Yeah, when they were publicizing this paper, they said, "Oh, look, an agent has discovered color transforms," and everyone just started, reacting, saying, "No, that if you include this in the action space and it uses it, it hasn't discovered anything." Right.
Yes.
So I think that's the gap between how they marketed this paper and the reality of what it actually achieves.
I was reading an interesting paper about architecture search instead of actually evaluating everything, learning a controller network that sort of predicts how an architecture will work. I think that would be interesting to see for augmentations as well, for a given data set. Yeah.
Yeah, that's actually kind of what I was referring to by surrogate. So instead of doing the actual evaluations, people just try to train simple models. Let's say, if I train just for 2 epochs, can you predict how it's going to do at, 200 epochs?
Yeah.
And then that surrogate essentially becomes, it's almost like a simulator, right? That surrogate becomes how you do the fitness evaluation, because these evaluations are just so expensive, to train a reinforcement learning agent on, right?
Yeah. Yep. Agreed.
Adrian, can you hear me?
Yeah.
Yeah. So I have a question on the sub policies. So they, you had that graph where they have number of sub policies versus the validation error. So their normal method is to just take like 5 sub policies, and so I guess is this graph basically changing it from 5 to any number on
Right.
this graph?
But they don't actually retrain with any number. They just say, okay, we have a pool of 500 good sub-policies, and then they draw subsets of, say, 40 of these and see how well they do.
Oh, okay. So they basically are just taking, so they have some pool of good policies, and then instead of taking, I guess, 5 sub policies, they would take, 40 or 50 or whatever.
Right.
Okay. Thanks.
Sure.
Adrian, I have a question.
Yeah.
Did they discover, like in the so in the policies, some of the transformations are I know they've been discretized, but some transformations are continuous. And in this kind of transformations, which can be in the continuous space, did you find like kind of like local minimas, or like regarding to a certain number there was it improved, and then after this certain number, then it starts to the error starts to go up again?
Yeah. Yeah, you certainly would expect it to be the case. Unless like the values which they find all tend to be like on the borders of these intervals. But I don't think, yeah, it would actually be, I think it would be a valuable result for them to report, for example, like what are in typical good policies, what are typical values of this magnitude here. I don't think they do that. I don't think they comment on this.
Thank you.
Sure. It's then, of course, also not clear that if the value that works well combined with many other transformations is also the value you want to use if you apply just that one transformation.
Yeah, sure. It must be a combination.
Any other questions? Well, if not, then apologies again for the slight delay at the beginning, and have a good evening, day, weekend.
Excellent job. You too, Adrian. Thank you so much.
Thanks.